is also classified as an unsaturated hydrocarbon. I'll explain that by looking at the empirical formula. You'll notice that the empirical formula is CnH2n. With an alkane, the empirical formula was CnH2n plus 2. So an alkene has fewer hydrogens as a result, and because of that, it is considered an unsaturated hydrocarbon. It does not have the maximum number of hydrogens that are available for a given number of carbons. And so in this particular case, we've got, in this example, we've got a 4-carbon structure which has 8 hydrogens as a result. If this was just an alkane, there would be 10 hydrogens. So this has fewer hydrogens in comparison, and it is unsaturated as a result. Now this empirical formula, where you just double the number of hydrogens, only applies to a hydrocarbon that has a single double bond. If you've got multiple double bonds, then you'd have fewer hydrogens still. Looking at the geometry of this molecule, the carbons involved in the double bond have a trigonoplanar geometry, yet the carbons that are at the end, the terminal carbons, still maintain that tetrahedral configuration. So how do you name the alkene? In this case, the root name is still using the same methodology. So you're trying to find the longest continuous chain of carbons, but this time you're trying to find the longest chain of continuous carbons that also includes the double bond. Now in this case, for the first structure, it's straightforward. There's only 2 carbons, so that the root name is eth. But it's the suffix that's going to change. The suffix is a reflection of the functional group. In this case, the suffix is going to be ene for the alkane, or for the alkene rather. So this is ethene. Here we've got a 3-carbon structure, and so the name of this is called prop-1-ene. And so you'll notice here that I'm now including a number to indicate where that double bond begins. This double bond begins at the very first carbon for propane, of my propane structure. Here I've got a 4-carbon structure, that's bute, where that double bond begins at the very first carbon, and so the name of the structure is but-1-ene. So any alkene has a suffix ene. Let's talk a little bit more about that numbering system. So again, the generic procedure for naming any organic molecules, you start with the longest chain of continuous carbons that must include the double bond. Then you indicate where that double bond is located, followed by the suffix. So but indicates that we've got a 4-carbon structure. The double bond begins at the very first carbon, and I know that it's a double bond because of the suffix of ene. And so when you're naming an alkene, you're always trying to give the double bond the lowest possible number. The double bond takes priority. So in this case, for the very first example, I will have to number the structure from right to left, because that way the double bond begins at carbon 1. And so this is 4 carbons, it's but, the double bond begins at carbon 1, so it's but-1-ene. In the next example, it's also a 4-carbon structure, but the double bond begins at the second carbon, and in this case, it doesn't matter if you number it from left to right or from right to left, the double bond would still begin at the second carbon, so this is but-2-ene. When you have branches, with the alkane, we were trying to give the numbering of an alkane was based on where the branch was located. In this case, the double bond will take priority. We try to give the double bond the lowest possible number first, and then consider the branches afterwards. So in this case, I'm going to number the first example from left to right. So I've got a 3-carbon structure with a methyl branch at carbon 2. So when you're including branches into your structure, the branches are added to the beginning of the name, just like how we are naming alkane structures. So 2-methyl prop-1-ene. In the next example, I've got a 4-carbon structure. I could number it from left to right, in which case the double bond begins at carbon 2. Or I could number this from right to left, in which case the double bond also begins at carbon 2. So no matter what naming method no matter what numbering technique I use in this case, the double bond will always start at carbon 2. So to help me break the tie, I'll consider the branch. And so if I use the numbering method in blue from right to left, the methyl branch begins at 2, which is a lower number than if I were to consider the numbering system from left to right. And so as a result, the methyl branch will be considered at carbon 2. It's a 4-carbon parent chain. That's bute with a double bond positioned at carbon number 2. 2-methyl-bute-2-ene. So again, when you've got a double bond with branches, they could be alkyl branches, they could be halogen branches, the double bond takes priority when you're trying to number your structure. Now let's take a look at alkenes that have multiple double bonds. When you have multiple double bonds, you will use a Greek multiplying prefix like you would with multiple branches of the same type. And you're again trying to choose the numbering system that gives the positions of those double bonds the lowest possible position that's available. So in the first example, it would make sense to start from left to right so that my very first double bond begins at carbon 1. If I went the other way, my very first double bond would begin at carbon 2 if I went from right to left. And so I'm going to choose the left to right numbering system as a result. And so in this case, I've got 2 double bonds, one that begins at carbon 1, the other one that begins at carbon 3. And so this is a 5-carbon structure. So it's pent with a double bond at carbon 1,3, so pent 1,3-diene, and then a methyl branch at carbon 4 as well. So 4-methyl, the branch goes at the front of the name, pent 1,3-diene, the Greek multiplier to indicate the fact that I've got 2 double bonds. You'll also notice that I've added an A after my root name here. So when you've got multiple functional groups, the A is added to the end of the root name. In this case, I don't have any branches with my second example, so it's a case of, should I number this from left to right or from right to left? So if I go from left to right, I've got double bonds beginning at carbon 1, carbon 3, and carbon 6. But if I choose the other direction, I have a double bond beginning at carbon 1, a double bond beginning at carbon 4, and a double bond beginning at carbon 6. So I need to once again apply the rule of first point of difference. The first double bond, there is no difference, but the position of the second double bond, there is a difference. I want to use the system that has the lower number. So I'm going to use the numbering system that is in blue. In other words, I'm going to number this from left to right. And so it's a 7-carbon structure, hept. I've got multiple double bonds, so I add an A at the end. Double bonds at carbon 1, 3, and 6, Greek multiplier, tri-ene. So again, when you've got more than one double bond, you have to add a letter A to the end of the prefix, buta, for example, or penta, or hepta. Let's talk about ring structures now. Ring structures, we're using the rules that we were using for cycloalkanes, but we're also using the rules for alkanes as well. When you're numbering a ring structure, you've got to number it so that the double bond has the lowest number possible. They take priority. When you're numbering a ring structure, carbon 1 and carbon 2, both of those 2 carbons have to include the double bond. If there is a tie when you're numbering a double bond, when you're trying to number clockwise or counterclockwise, use branches to break your tie. So for example, I could go clockwise, so in which case this would be my first carbon and my second carbon would be here. So again, carbon 1 and carbon 2 must both contain the double bond, and then this would be carbon 3, carbon 4, carbon 5, and carbon 6. Alternatively, I may want to consider numbering this counterclockwise, in which case the first two carbons again have to include the double bond. So this would be carbon 1, this would have to be carbon 2, 3, 4, 5, and 6. So in both numbering systems, the positioning of the double bond is identical, so the branching system will help me break the tie. And you can see that my two methyl branches, when numbering clockwise, begin at carbon 3 and 4. That's a lowering numbering system. That's what I'll use. So this is 3,4-dimethyl cyclohexene. Now you'll notice in this case that the numbering of my double bond isn't included. It's not cyclohex-1-ene. This is tricky. If you recall with the cycloalkanes where there was one branch, the numbering position of that branch wasn't included. It was implied. So if you've got a single double bond in a ring structure, you do not have to indicate the position number because it's implied. The positioning of the branches, however, are not implied, so you do have to include those numbers. When you've got multiple double bonds, the positions of those double bonds are not implied. So in this case, we would have to include the position numbers of those double bonds. So again, it's a case of, should I be numbering this clockwise or counterclockwise? So let's start with going in the clockwise direction. I'm trying to give my double bonds priority as having the lowest possible number. So this would be carbon 1. The second carbon would have to include the double bond. And so I'd have a double bond beginning at carbon 1 and beginning at carbon 3 if I went clockwise. If I went counterclockwise, making sure that my double bonds have the lowest possible number, so it wouldn't make sense to start here as being carbon 1, because then my second double bond would be much further down. So I'm going to start numbering here as being carbon 1. That way my second double bond will have the lowest possible number. So clockwise or counterclockwise, the positions of my double bonds are identical. They both start at carbon 1 and carbon 3 regardless. So it's going to be the branch that's going to help me decide which direction I'm going to use. So my methyl branch has a lower number at carbon 5 when I'm going counterclockwise, and that's the technique that I'm going to use. So the name of this structure, methyl branch at carbon 5, it's a ring structure, cyclo, it's 6 carbons, hex, it's got multiple double bonds, so I add the A, and the double bonds are located at carbon 1 and 3. Greek multiplier for the double bonds, I've got 2 double bonds, so it's a Greek multiplier of di with a suffix "ene." That is a difficult question. This is the hardest possible question I can think of. Pause the video here, try and name it. I'm basically throwing every single rule I can at you when I came up with this problem. So pause the video, let's see what we can do, let's see what you can do, and we'll take this up. Okay, how on earth are we going to name this? The idea here is to start with the double bonds. Give priority to those double bonds. So the question is, do I go clockwise? In which case, if I go clockwise, this will be the best way. I'm trying to give my double bonds the lowest possible number. Or do I go counterclockwise? And if I go counterclockwise, it would make sense to start with my numbering system here. Again, I'm just trying to give priority to those double bonds, making sure that the double bonds have the lowest possible number. So those are my two choices that result in my double bonds having the lowest position. So it's going to be the branches that have priority. So if let's start with the counterclockwise. So I've got my double bonds are both, my double bonds are at carbon 1 and 3, and then I've got branches at carbons 1, 2, 3, 4, 5, and 6. I've got branches at every single carbon. If I consider the clockwise direction, again, I've got a double bond starting at carbon 1 and carbon 3, so that's a tie. And I've got double bonds at carbon 1, 2, 3, 4, 5, and 6. So it would seem like there's no first point of difference whatsoever. Whenever that's the case, we go with alphabetization of my branches to break the tie. So at carbon 1, my very first branch is an ethyl branch. No, that's not true. At carbon 1, I'm looking at the wrong numbering system. At carbon 1, my very first branch is a methyl branch. It starts with the letter M. But when I use the other technique, when I'm numbering this in counterclockwise, carbon 1, my very first branch is an ethyl branch. So if there's something that's different, I'm going to go with the ethyl because that's lower down on the alphabet. Alphabetization is what's going to break my tie. So I'm going to be numbering this in a counterclockwise direction. So I've got an ethyl branch here, a methyl branch here, a propyl branch, another methyl, another ethyl, and yet another propyl. So let's start with the branches. I'm going to list my branches in alphabetical order. So I've got ethyls at carbons 1 and 5. So I've got 1, 5 diethyl. Then next in the alphabetization rule is going to be my methyl branches, which start at carbons 2 and 4. So notice that I'm separating letters and numbers by hyphens, and numbers are being separated by commas. 2 of those, dimethyl. And then last is my propyl branches, which start at carbon 3 and 6. Okay, so I've now listed all of my branches. Now it's time to name the ring structure. It is because it's a ring, it's cyclo, it's 6, so it's hex. It's got multiple double bonds, so I bring in the A, and those double bonds are positioned at carbon 1 and 3. 2 double bonds, so a Greek multiplier for the double bond, and then the suffix for the double bond is -ene. 1,5 diethyl, 2,4 dimethyl, 3,6 dipropyl, cyclohexa, 1,3 diene. That is by far the hardest question that I can come up with for alkenes. Okay, let's try something else here. Let's try drawing alkenes. So cyclopentene, first of all, it's a 5-carbon ring structure. It doesn't tell me where the double bond is positioned, so it's implied to be at carbon 1. So you can draw that ring. When you draw the ring, you can put the double bond wherever you want. I put it up here. You could put it down there, wherever you want. It doesn't matter, but wherever you put it, that has to be considered position number 1. Okay? So in this drawing, I put the double bond here, which means this has to be carbon 1, which means this would have to be carbon 2. Again, the carbon 1 and carbon 2 have to include the double bond. And then here's carbon 5. 3-methylpropyl octa 2,4-diene. This is not a cycloocta, so this is just an 8-carbon chain. Again, you choose if you want to number it from left to right or from right to left. So here, this is going to be carbon 1, 2, 3, 4, 5, 6, 7, 8, with a methyl at carbon 3 and a propyl at carbon 4. Okay, take a few minutes and draw these. And again, pause the video. Once you've got the drawings, let's take these up. Okay, so let's take up 1,2,3 trimethyl cyclohexaone-3-diene. That just rolls off the tongue nicely, doesn't it? So it's cyclohexa, so that's going to be a 6-carbon ring structure with double bonds at carbon 1 and 3. It doesn't matter where you choose to draw the double bonds, but wherever you do, that's going to decide how you number it. Okay, so in this case, I'm using a complete structural diagram. So carbon 1, 2, 3, 4, 5, and 6. Here's my ring structure here with a methyl branch at carbon 1, 2, and 3. So you can see why the complete structural diagrams aren't always drawn. They're hard to interpret, but here's another way of drawing it. Let's try that again. All right. Okay, so I'm going to draw it differently here. I'm going to put the branch. I'm going to make this carbon 1, this carbon 2, which means that this is carbon 3 here. And so I'm going to need a methyl branch here, a methyl branch there, and a methyl branch here. So these are the exact same structure. This one has just been flipped vertically in comparison to that one. 3-methyl pentene, pardon me. Okay, so here's carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Carbon 1, 2, 3, 4, and 5. Pentene, the double bond is there. So this is carbon 1, 2, and here's carbon 3, 4, and 5 with my methyl branch at carbon 3. You'll notice that when it's not a ring structure, the numbering system must be included. It's only with ring structures that have a single double bond where you do not need to include the position number of the double bond. In the next video, we will talk about cis and trans geometry.